Hello, everybody. I welcome you all to another episode of readingbeachdev.net. No, wait, beach.us guide articles for learning C. This is the 20th article. I did say we had a break. We're going to break it. We're going to stop the article and read other topics. But because of the comment here, because of the comment shown on the screen, I was motivated to do more articles on this, right? I was like, you know what? Let's go. Let's just start doing it. From just one comment, I am very positively reinforced by social interactions, even if it's online. All right. So let's start then. Go CPC LS CD CD, what was it? CD beach. That okay, make directory. Where is more fun with structs? Okay, so structs 2 CD structs 2, my gang. Let's go. So turns out there's a lot more you can do with structs than we have talked about, but it's just a big pile of miscellaneous things. So we'll throw them in this chapter. If you go to Start Basic, you can round out your knowledge here. Initializers of nested structs and arrays. Remember how you could initialize struct members along these lines? Yep. Turns out we have more power in these initializers than we originally shared. Exciting. For one thing, if you have a nested substructure like the following, why is it a substructure? Like the following, you can initialize members of that substructure by following the variables down the line. Okay, how is it a substructure? Yeah, looking at the following example. So hash include studio.h, struct cabin information, int window count, struct spaceship, manufacturer, cool. So struct spaceship s is equal to dot manufacturer is equal to general product and products dot cy dot window count is equal to 8 nested initializer. Oh, what is this? Oh, struct cabin information CI. Oh, okay, cool. Print oxygen. I see. Check out lines 16 to 70. That's where we are initializing members of the struct cabin information in the definition of S, our struct spaceship. And here is another option for that same initializer. This time we'll do something more standard looking, but either approach works. So this is our standard, yeah, they make more fucking sense than whatever this was. Now, as if the above information is spectacular enough, we can also mix in array initializers in there too. Let's change this up to get an array of passenger information in there, and we can check out how initializers work in there too. So struct in name COVID vaccinated boolean hash define max passengers, and then we have a passenger where passenger is an array of passengers, and then dot passenger is equal to initialize a field at a time. What the hell? Dot name is equal to greatly do is dot COVID vaccinated, because those two are the variables, and or all at once. Oh, you can do initialize at a time or all at once. Nice. Print passengers as passenger appetite name, code name. Okay, that is cool. So anonymous structs. Now these are the structs with no name. We also mentioned these in the type def section, but we'll refresh here. Here's a regular struct with the name and shit, and here's the anonymous equivalent. Okay, so we have a struct, but it has no name. We have no way of using it later. Seems pretty pointless. Admittedly, in that example it is, but we can still make use of it a couple ways. One is rare, but since the anonymous struct represents the type, we can just put some variable names after it and use them. So no name, 3 variables over this struct type, a.name antelope, c.like count, for example. But that's still not that useful. Far more common is use of anonymous structs with a type def so that we can use it later, example, to pass variables to functions. Oh, far more common use of anonymous structs with a type def so that we can use it later, example, to pass variables to functions. So type def struct No name, star name, ba ba ba, new type, animal. Animal ABC. Personally, I don't use many anonymous structs. I think it's more pleasant to see the entire struct animal before the variable name in the declaration, but that's just like my opinion, man. Self-referential structs. Now, for any graph-like data structure, it's useful to be able to have pointers to the connected nodes or vertices. But this means that the definition of a node, you need to have a pointer to a node. It's chicken and eggy. But it turns out you can do this in C with no problem whatsoever. For example, here's a linked list node, struct node, data, and next. It's important to note that next is a pointer, which is what allows the whole thing to even build. Even though the compiler doesn't know what the entire struct node looks like yet, all pointers are the same size. Here's a cheesy linked list program to test it out. Yeah, I actually set up a linked list. Yeah, I used to do this while I was in college. Traverse it, makes sense. Flexible array members. Back in the good old days, when people carved C code out of wood, some folks thought would be neat if they could allocate structs that had variable length arrays at the end of them. I want to be clear that the first part of the section is the old way of doing things, and we're going to do things the new way after that. For example, maybe you could define a struct for holding strings and the length of that string. It would have a length and an array to hold the data, maybe something like this. But that has a 8 hard-coded as the maximum length of a string, and that's not much. What if we did something clever and just malloc some extra space at the end after the struct and then let the data overflow into that space? Let's do that and then allocate another 40 bytes on top of it. So it takes the size of star s plus 40. What is s here? I mean, what is this s doing here? I mean, no. If you go back to the malloc article, you can see that it can take the size. Like it can take the size of the it can take the size of this thing as well. Because data is the last field of the struct, if we overflow that field, it runs out into space that we already allocated. For this reason, this trick only works if the short array is the last field in the struct. Oh. So he added 40 bytes to it. Copy more than 8 bytes. Won't cache, probably. In fact, there was a common compiler workaround for doing this, where you allocate a zero length array at the end. And then every extra byte you allocated was ready for use in that string. Because data is the last field of the struct, if we overflow that field, it runs out into space that we already allocated. Whoa. But of course, actually accessing the data beyond the end of that array is defined behavior. In these modern times, we no longer deign to resort to such savagery. I can show you the project, by the way. Nigando and dot it out, and what was that word? Deign. Work, do something that one considers to be below one's dignity, right? So yeah, it uses the word net. Oh my god, that sound. I need to really change that sound. It uses the WordNet's dictionary files, the database files, and passes through all of that. But of course, actually accessing the data, yeah. And we no longer deign to resort to such savagery. I think that's how you spell it, pronounce it. Luckily for us, we can still get the same effect with C99 and later, but now it's legal. Let's just change our above definition to have no size for the array. Again, this only works if the flexible array member is the last field in the struct, and then we can allocate all the space we want for those strings by mallocing larger than the struct length string, as we do in this example that makes a new struct length from a C string. So a struct length string, it prints out a pointer to a struct length string, and it takes in a pointer to a character, an array of characters. Basically, it takes the length of the string, allocate len more bytes than we normally need. That's what they basically did in their previous case. And then ls length equals len, and then copy the whole fucking thing to ls data. Padding bytes. Now, beware that C is allowed to add padding bytes within or after a struct as it sees fit. You can't trust that they will be directly adjacent in memory. Yes. I think what it was, I think I've heard this in college as well and some YouTube shorts. So what it means is that it takes in the highest character. Suppose say integers. So integers is 4 bytes, right? And we have a character. Character is 1 byte. But the character will actually fill 4 bytes. 4 bytes. The struct itself will be encompassing 8 bytes, because the largest guy is 4 bytes, right? And that much bytes is given to the character member as well. I think that's what he's going to say. Don't take my word for it, because I'm still a beginner in this. Let's take a look at the program. We output two numbers. One is the sum of the size s of the individual field types. The other is the size of the entire struct. One would expect them to be the same. The size of the total, the size of the sum of its parts, right? Yeah. So by my definition, by my explanation, it should be int a. So 16 bytes. There you fucking go. So yeah, so I was correct. So size of, and the unsigned integer, I mean for the size of type. So, but on my system, this outputs, they are not the same. The compiler has added 6 bytes of padding to help it more performant. Maybe you got different output with your compiler, but unless you're forcing it, you can't be sure there is no padding. Offset off. In the previous section, we saw that the compiler could inject padding bytes at will inside a structure. What if we needed to know where those were? We can measure it with offset off defined in stdef.h. Let's modify the code from above to print the offsets of the individual fields in the struct. So yeah, the offsets here were a is 0. That makes sense. Wait, what? Could inject padding bytes at will inside the structure. What if we need to know where those were? We can measure it with offset off. Oh, okay. Where those are? Indicating that we are using 4 bytes for each of the fields. Yeah, it's a little weird because char is only 1 byte, right? The compiler is putting 3 padding bytes after each char so that all the fields are, yeah, I'm not getting it still. All the fields are 4 bytes long. Presumably this will run on my faster on my PC CPU. So wait, I don't understand this. Indicating that we're using 4 bytes for each of the fields. Okay, A does not have anyone. A is static. I think I get what he means. So A is there, and then after 4 bytes, B starts, and after 4 bytes, C starts, and after 4 bytes, so that's what offset off does. Offset off does not show you how much was added. In my mind, I assumed that offset off adds, even though it doesn't sound like a function that shows you how much has been added, it's a function that shows you the offset. It makes so much fucking sense now. Oh my god, I don't know why I was tripping there. Fake oop. Now, there's a slightly abusive thing that's sort of oop-like that you can do with structs. Since the pointer to the struct is the same as a pointer to the first element of the struct, yeah, you can freely cast a pointer to the struct to a pointer to the first element. Freely cast a pointer to the struct to a pointer to the first element. What this means is that we can set up a situation like this: parent and super must be first. Then we are able to pass a pointer to a struct child to a function that expects either that or a pointer to a struct parent. Because struct parent super is the first item in the struct child, a pointer to any struct child is the same as a pointer to that super field. Oh, that's a cool way to do it. My internet is fucky. No, super isn't a keyword. Incidentally, we're stealing some OOP technology. Okay, yeah, that makes sense. Let's set up an example here. I will actually do this. I am interested in seeing oop.c. So yeah, hash include studio.h and struct parent, do this, and int a b struct child. Then we have a super parent that is a pointer to the parent, and then int c and d, and making the argument void star so we can pass any type into it, namely a struct parent or struct child. Void print parent void star P. Nope, don't do that. Yeah. So struct parent self print parent, by the way, P, right? So it typecasted, not typecasted, it casted to the parent pointer, expects a struct pointer, but a struct child will also work because the pointer points to the struct parent in the first field. I got you now, gang. I got you now. Printf parent. Wait, yeah, do this. Nope, 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 nope. I wonder what I did there. D slash n self a self b. Okay, void print child struct child star self. Oh, I'll get copyrighted. Oops. Copyright is not good. I guess I don't give a shit if I get copyrighted. Tamina tamina. Africa. I love that song. Cool song. Brings back memories, not gonna lie. If I get copyright stricken, I'll remove this part. If I just get a demonetization or some shit like that, I'm not even registered to the fucking payment mode. I don't know what I'm yapping. So yeah, this print child, it needs the child pointer and boomy boom, do that. Now int main void boomy struct child c is equal to dot super dot a equals 1 and dot super dot b equals 2. That's so fucking cool. Dot c equals 3 and dot d equals 4. And then print the child, give me the pointer to that fucker, and print the parent. And that is also, oh, not dollar sign. Where's ampersand? Yeah, C. Yep. And yeah, boom, 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 CCT, oop dot C, and he expects an identifier there. Oop dot C. Yeah, makes sense. Expected, yeah, C. Let's see, and boom. There you go, child 3, 4, parent 1, 2. See what we did on the last line of main? We called print parent but passed the struct child star as the argument, even though print parent needs the argument to point to a struct parent. We're getting away with it because the first field in the struct child is the struct parent. Again, this works because a pointer to a struct has the same value as a pointer to the first field in that struct. This all hinges on the this part of the spec. A pointer to a structure object suitably converted points to its initial member and vice versa. An object shall have its stored value accessed only by an L-value expression that has one of the following types. A type compatible with the effective type of the object, and my assumption that suitably converted means cast to the effective type of the initial member. So I get this. An object shall have its stored value accessed only by an L-value expression that has one of the following types, a type compatible with the effective type of the object. Okay, makes sense. Bit fields. So what this means is you can only access the stored value if its L-value expression, if it's the left-hand side value of expression is effectively to the same as the effective type of the object. Yeah, bit fields. Now, in my experience, these are rarely used, but you might see them out there from time to time, especially in lower level applications that pack bits together into larger spaces. Let's take a look at some code to demonstrate a use case. So unsigned integer a, b, c, d. For me, this prints 6, which makes sense since unsigns are 4 bytes on my system. But what if we knew that all values that were going to be stored in A and B could be stored in 5 bits, and the values in C and D could be stored in 3 bits? That's only a total 16 bits. why have 128 bits reserved for them if we are going to only use 16? So yeah. Well, we can tell C to pretty please to try crack these values in. We can specify the maximum number of bits that values can take from 1 up to the size of the containing type. Oh, we do this by putting a colon after the field name followed by the field width in bits. So 5 bits here, 5 bits here, and 3 bits in 3. Now when I ask C how big my struct 4 is, it tells me it's 4. That means it was 16 bytes, but now it has only 4 bytes. That means 4 into 8 is 32. Let us pack those 4 values down into 4 bytes, which is a 4-fold memory savings. Trade-off is of course that the 5-bit fields can only hold values from 0 to 31 and the 3-bit fields can only hold values from 0 to 7. But life's all about compromise after all. So why is it 4 bytes? I thought it would be 16 bits. So that would be 2 bytes. Is it because 5 bits? We do this by, okay, I guess 4 bytes. So 1 byte in here, 1 byte in here, 1 byte in here, 1 byte in here, is it not in here. 4 into 8 is 32 because 32 bits we have. We don't need 32 bits, we only need 16 bits, right? Am I missing something? So this will be 1, not 1. This and this will be 2 bytes, 1 byte, and this will be 2 bytes. I mean 1 byte, 1 byte. So I wonder why it's 4. If any C professionals out there, why this is 4 bytes instead of 2 bytes? Please do say. Non-adjacent bit fields. I gotcha. C will only combine adjacent bit fields. If they are interrupted by non-bit fields, you get no savings. For me, since A is not adjacent to C. Now, in that example, since A is not adjacent to C, they are both packed in their own ints. So we have one int each for A, B, C, and D. And since my ints are 4 bytes, there's a grand total of 16 bytes. A quick arrangement yields some space saving from 16 bytes down to 12 bytes on my system. So this means 1 bit, right? Or is it 1 byte? No, I think it's 1 bit. And now since A is next to C, the compiler puts them together into a single int. So now, so we have, oh, is that the reason why? It's bundling them together. So A needs 5 bits, right? Total 1A can have 4, not bytes, 4 bytes, right? So that's why this became 16 bytes. So normally it's 4 bytes. Now in 4 bytes, how much we have? We have 8 bits. So out of that 8 bits, A encompasses 5 bits or consumes 5 bits. So we have 3 left. Now that is B cannot do that. So I think C is the one that's going to do it. Actually, no. And remaining 3 are there. I think 3 is vacant. Most likely 3 is vacant. So that is 8 bits right there. Right? So that's 1 byte. And next 5. Next 5 we have, and that is also 8 bits. 8 bit. Okay, that's 1 byte. We have 4 bytes space. Wait, let me rethink this. So let's just take one integer. One integer has 4 bytes, right? And 4 into 8, that is 32 bits for one integer. Now if I take 5 bits of that, that's good. And I take 5 bits of that. But because you can't, you have to separate it. So I take 8 bits. I take 8 bits out because the 5 is there. So that's 1 byte. And I take another 8 bits because the 5 is there, that's 2 bytes. And I take another byte, that is 3 bytes, so total, because 3 and then another 3. So shouldn't it be 3 bytes instead of 4 bytes? I wonder why. Because 3, 3, it's 6, right? Or should it be same? 5 is there, 3 is left. 5 is there, 3 is left. And 3 is there, 5 is left. And 3 is there, 5 is left. That doesn't make any sense. I wonder why it's like that. So non-adjacent can't do that shit. And now since A is next to C, the compiler puts them together into a single integer. Now we have one int for a combined A and C and one int each for B and D for a grand total of 3 ints or 12 bytes. Oh, is it something like that? Okay, so the int so these two guys are together. I mean, one int, that's what I'm thinking, like 5 here, and you can't combine this fucker with this. So 1 here, 1, this should be 1. It's still 3, my gang. I don't know why. I don't know how you got 4 bytes. Should I check it? So what is this called? Bitfield. Bit.c hash include studio.h struct for unsigned integer A and it's 5 bits. Unsigned integer A, not A, B, it's 5 bits. An unsigned integer C and it's 3 bits. An unsigned integer and it's 3 bits. Right? Now void main void printf percentage u slash n size of struct for boomy fuck off cc. Oh no, there you go. What do you mean? Bit.c. Who's fuck you, man? Fuck that shit. Fuck that. Bit.c. And then do this. It's still 4, and I don't get it how it's 4. Okay, you know what? I'm going to remove one of them. I'm going to go on the bottom of this pit. What? I'm going to go bottom of this. I feel like I am lacking a word there. cc bit.c and do this. It's still 4 bits. I mean 4 bytes. How is it 4 bytes? I removed one of the cut that part out. I don't want everyone canceling me and looking at my looking up my profiles and shit. So yeah, cut that out. I don't want to spread like that shit. Yeah. So I feel like I feel like something is missing here. So yeah, and now since grand total of 3 ints, now we have 1 int for a combined A and C. How is it 1 int, my gang, and int each for D and E? Now signed or unsigned. Now if you just declare a bit field to be int, the different compilers will treat as signed or unsigned, just like the situation with car. Be specific about the signedness when using bit fields. Oh, I have forgotten what was the situation with car. Unnamed bit fields. In some specific circumstances, you might need to reserve some bits for hardware reasons, but no, there it is. But no need to use them in code. For example, let's say you have a byte where the top 2 bits have a meaning, the bottom 1 bit has a meaning, but the middle 5 bits do not get used by you. So we could do something like this: unsigned character A 2 bits and dummy 5, and that works. In our code we use A and B but never dummy. It's just there to eat up 5 bits to make sure A and B are in the required by this contrived example positions within the byte. C allows us a way to clean this up: unnamed bit fields. You can just leave the name dummy out in this case, and C is perfectly happy for the same fact. Oh, that's clever. 0 with unnamed bit fields. How many is there? 20.10, 20.11. Okay, let's go. With unnamed 0. Now, some more esoteric out here. Let's say you are packing bits into an unsigned integer and you needed some adjacent bit fields to pack into the next unsigned integer. That is, if you do this. Now the compiler packs all these into a single unsigned integer. But what if you needed a and b in one integer and c and d in different one? There's a solution for this. Put an unnamed bit field of width 0 where you want the compiler to start anew with packing bits in a different integer. Okay. It's analogous to an explicit page break in a word processor. You're telling the compiler stop packing bits in this unsigned and start packing them in the next one. By adding the 0 with named bit field in that spot, the compiler puts a b in one signed integer and c and d in another signed. So 2 total for a size of 8 bytes on my system. Unsigned ints are 4 bytes each. Still don't get how that is 4 bytes. Unions. Now, these are basically just like structs, except the fields overlap in memory. So the union will be only large enough for the largest field and you can only use one field at a time. It's a way to reuse the same memory space for different types of field. You can declare them just like structs, except it's union. Take a look at this. So now that's a lot of fields. If this were a struct, my system would tell me it took 36 bytes to hold it all. But it's a union. So all those fields overlap in the same structure of memory. The biggest one is int or float, taking up 4 bytes of my system. And indeed, if I ask for the size of the union foo, it tells me 4. So the trade-off is that how you can probably use one of those fields at a time. Oh, you can only probably use one of those fields. Now, however, unions and type tuning. You can non-portably write to one union field and read from another. Doing so is called type tuning. Supports or circumvents the type system in order to achieve an effect that would be difficult or impossible to achieve within the bounds of the formal language. Time punning or puning, I don't know. And you use it if you really knew what you were doing, typically with some kind of low-level programming. Since the members of a union share the same memory, writing to one member necessarily affects the others. And if you read from one what was written to another, you get some weird effects. So union foo is short b is there and short a is there, and union foo x dot b equals 3.1414159 and printf. Fair enough, but what about this? Now on my system this prints out because under the hood the object representation for float was the same as the object representation for the short 4048. On my system your results may vary. Okay. Oh. Okay, that makes sense. Now, if you have a pointer to union, you can cast that pointer to any of the types of the fields in that union and get the values out that way. In this example, we see that union has ints and floats in it. And we get pointers to the union, but we cast them to int star and float star types. The cast silences compiler warnings. And then if we dereference those, we see that they have the values we stored directly in the union. Whoa! So int, no, wait. Okay, so I take the pointer and I int star it, and if I do dereference it, I get 12 again. Whoa. So the reverse is also true. If we have a pointer to a type inside the union, we can cast that to a pointer to the union and access members. So we have union foo and we take the pointer foo star and then we convert that pointer. That pointer to union foo star to get union foo star back to pointer to union. So this list line the same as this one. Oh, nice. All this just under the hood, all these values in a union start at the same place in memory, and that's the same as where the entire union is. Common initial sequence in union. Now, if you have a union of structs and all those structs begin with a common initial sequence, it's valid to access members of that sequence from any of the union members. What? Yeah, exactly. If you have a union of structs, and all those structs begin with the common initial sequence, it's valid to access members of that sequence from any of, oh, it's valid to access members of the sequence from any of the union members. So here are two structs with a common initial sequence. Float, map. Do you see that? It's that they started in followed by float. That's the common initial sequence. The members in the sequence of the structs have to be compatible types, and we see that with x and y, which are integer and float respectively. Now let's build a union of these. What this rule tells us is that we have guaranteed that the members of the common initial sequences are interchangeable in code. That is, f.sa.x is the same as f.sp.x and f.sa.y is the same as now, because fields x and y are both in the common initial sequence. So also, the names of the members in the common initial don't matter. All that matters is that types are the same. Altogether, this allows us a way to safely add some shared information between structs in the union. Oh, so the best example of this is probably using a field to determine the type of struct out of all the structs in the union that is currently in use. That is, if we weren't allowed this and we passed the union to some function, how would that function know which member of the union was the one it should look? Take a look at these structs, note the common initial sequence. So common, antelope type. So type common initial sequence, int C creature. Okay, this is the one. Now let's throw them into a union. Also, please indulge me, these two hash defines to the demo. So far nothing special has happened. It seems like the type field is completely useless. But now let's make a generic function that prints a union animal. It has to somehow be able to tell if it's looking at a struct antelope or a struct octopus. Now because of the magic of common initial sequences, it can look up the animal type in any of these places for a particular union animal x. So x.common.type, all those refer to the same value in memory. And as you might have guessed, the struct common is there, so code can agnostically look at the type without mentioning a particular animal. So look at this code to print a union animal. So we have antelope type. Okay, so they can be different values, although they have to be the same value. So now if it's an antelope, we take that octopus, and that's common between all the structs. See how on line 29 we are just we're just passing in the union. We have no idea what type of animal struct is in use within it, but that's okay, because on line 31 we check the type to see if it's an antelope or an octopus, and then we can look at the proper struct to get the members. It's definitely possible to get this same effect using just structs, but you can do it this way if you want the memory saving effects of a union. Nice. Unions and unnamed structs. Now you know how you can have unnamed struct like this that defines a variable s that is anonymous struct type, because the struct has no name tag with members x and y. So things like this are valid, s.x. Yes, turns out you can drop those unnamed structs in unions just like you might expect. So yeah, and then access them as per normal. No problem. Nice. Passing and returning structs and unions. Now, you can pass a struct or union to a function by value as opposed to a pointer to it. A copy of that object to the parameter will be made as if by assignment as per usual. You can also return a struct or union from a function, and it is also passed by value back. So it copies the value. So struct foo f void, and f copy is made of, because who's f? Yeah, it returns a copy of this. Fun fact, if you do this, you can use the dot operator right off the function call, because of course that example calls the function twice inefficiently. And the same holds true for returning pointers to structs and units, just to be sure to use the operator in that case. Yeah, because indirection pointer. So that's about it for article 20. Thank you for the motivation from this comment, right? So I will be continuing this series. Back then I reached till 19. So to follow tradition, we're going to do this till 29. Oh, I feel like 29 is a juicy one. So that's about it for structs and more. Bye. About the project update, I'm going to put this in the last. I have put, what do you say? I have created the project and it is there in my GitHub. What it mostly does is right now goes through the dictionary files and prints out the meanings. There are some bugs, there are some meanings that cannot be received, not received. There are places where the meanings are not cannot be extracted, or sometimes null pointers get printed, right? There are bugs such and such like that. I did also plan to make it sort of like a program like dictd, but then I procrastinated about it a lot, and I had other stuff to do like my work and also try to learn about low level stuff, especially reverse engineering. So I kind of forgot about this, and then I lost interest in doing it. So I abandoned the project, right? Maybe in the future I might get interested in doing it, maybe after knowing about C a lot, right? I might get interested in doing the project again. But until then, let's just move on with the article.